Hello everyone, in this video we are going to be solving a definite integral using the limit definition. So before we get started, let's review the theorem real quick. If f is integrable on a closed domain a to b, then the integral of f of x from a to b is equal to the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x, where delta x is equal to b minus a over n, where b and a are the limits of integration, and x sub I is equal to a plus I delta x. Now keep in mind, this I is not the complex I. So if this is squared, it's not going to be square root of -1 squared, which is -1. So just don't think about complex when you're doing this. For reference, you have these sums of powers for I in this context. So we have the sum over 1 for I equals 1 to n is equal to n. For I, it's n times n plus 1 over 2. And then so on for I squared and I cubed. We have these here for reference. So the integral we're going to be looking to solve is, we want to find the integral of x squared minus 4x plus 2 from 1 to 4 using the limit definition. So before we get started, let's go ahead and identify our delta x and our x sub I. So our delta x is going to be the upper limit of integration, b, minus the lower. So that's going to be 4 minus 1 all over n, which is equal to 3 over n. Our x sub I is going to be equal to the lower limit of integration, which is a, so 1, plus I times delta x, which we found to be 3 over n. Now, using this definition up here, you see this is a summation of f of x sub I times delta x. So we're going to plug this x sub I into our function, right? So essentially what we're doing is we have a function f of x. So we're doing the integral of 1 to 4 of f of x dx. So that means our f of x is equal to x squared minus 4x plus 2. But, looking up here at the theorem, we want f of x sub I. So everywhere there's an x, we're just going to plug in the x sub I, which is what we found here, okay? So then to create f of x sub I, we have f of x sub I is equal to x sub I, so 1 plus I times 3 over n, all squared, minus 4 times 1 plus I times 3 over n, plus 2. That's our f of x sub I. And then for the definition, which we have up here, we're going to end up multiplying this by the delta x when we write it out. So now let's write out this side, the right-hand side of this definition. So that is going to be, so this integral is going to be equal to the limit as n goes to infinity of the sum over I equals 1 to n. And now everything is going to go in. We're going to open up a big brace here, bracket, and we're going to put in our f of x sub I. So I can just copy and paste this in. okay? And then we want to multiply this whole thing by our delta x, as you see here. So our delta x we found to be 3 over n. So this is multiplied by 3 over n. All right, so right off the bat, we can move this 3 over n to the front, in front of this summation, because this is not dependent upon I, but it has to stay within the limit because the limit is over n. All right, so on the next line down, we are going to move that 3 over n over, and then we are going to expand this term and then distribute this 4 into this term, okay? So that's what we're doing on the next line. So then we have the integral is equal to the limit as n goes to infinity times 3 over n times the summation over I equals 1 to n. Open up big bracket, parenthesis, whatever you want to use. Now, this first term expands out to be 1 plus 6i over n plus 9i squared over n squared. And then when we distribute this 4 into each one of these terms in the expression, we end up with a negative 4 minus 12i over n, and then we add our 2. Okay, so now what we're going to do is we're going to combine like terms. So we have a 6i over n, a minus 12i over n. We have some constants here, 1, 4, and 2. And this one is by itself, right? So we can combine those on the next line. And we still can't do anything with this 3 over n yet because we're still trying to figure out some stuff in here. So moving down to the next line, we have the limit as n goes to infinity of 3 over n times the summation I equals 1 to n of the term, of the quantity, whatever you want to use to describe it. And then combining these terms, we end up with a negative 1 minus 6 over n I plus 9 over n squared I squared. Now you notice I wrote these i's. They're off to the side of the fraction, but they're still multiplied by the numerator, of course. But I did these that way we can come back to these references, right? So you can multiply these by a constant, right? And it's still going to be the same because you're summing over I. As if you recall from the summation, from properties of summations, you can pull a constant out and put it in front of the summation. So that's what I'm going to do here. So in the eyes of this summation right here, it's going to n, but it's not summing over n. It's summing over I, okay? So that means our next line, I'm going to go ahead and move the summation into each term so we can readily identify it with the references above. So we have the limit as n goes to infinity of 3 over n times a negative summation of I equals 1 to n, 1 minus 6 over n times the summation of I equals 1 to n I plus 9 over n squared times the summation of I equals 1 to n of I squared, and then close parentheses, bracket, whatever you want to use. Now, I did that so it's easy to see that here, right here, sum over 1, that's just going to be our n. Sum over I, that's going to be this term. And then sum over I squared is going to be this term, okay? So now we plug those in. And we get the following. The limit as n goes to infinity times of 3 over n times, so this is a negative n, and then we have minus 6 over n times n times n plus 1 over 2 plus 9 over n squared times, now you can put parentheses in here if you need to, or you can put them here if you need to, whatever helps you understand what you're writing. As long as it's legal to put it in there and you're not grouping something that's not supposed to be grouped, then you're fine. So then we have 9 over n squared times n plus 1 times 2n plus 1 all over 6. And then close parentheses, bracket, whatever you're using. All right, so next line down, we're going to do a little simplification. Now you can simplify it faster, slower than I do. I'm just doing it this way so it's easy to follow. So we have the limit as n goes to infinity of 3 over n times, let's see, we have negative n minus 3n minus 3 plus, now I'm going to, so I expanded this out, these terms out separately, so I didn't have to waste a lot of time in the video doing it. But I suggest you take the time to expand this out and find that when you expand this term out right here, you end up with a 2n cubed plus 3n squared plus n. That's what that n times n plus 1 times 2n plus 1 expands out to be. So then we have minus 3 plus 6n cubed over 2n squared plus 9n squared over 2n squared plus 3n over 2n squared. Now, you may notice that the denominator is all 2n squared. So what I did is that blue term that I had over here, for this thing expanded out, I multiplied, so 9 over 6 is going to be 3 over 2. So you have 3 over 2n squared. So this ends up being 3 over 2n squared multiplied by this whole expanded term, right? So what I'm doing is I'm multiplying these things in and then breaking them out as separate fractions so they're easier to work with, since I only have one term in the denominator. So then next we are going to do some simplification. And we have the limit as n goes to infinity of 3 over n times, this comes out to be negative 4n minus 3 plus 3n plus 9 over 2 plus 3 over 2n. Like I said, you can simplify faster or slower if you want. This is just how I did it, and this is how I'm doing it for the video. So next, we're just going to continue to simplify things and combine some like terms here. So the limit of 3 over n times, let's see, we have minus n plus 3 over 2n minus 6 over 2 plus 9 over 2. And then just a couple more lines left. So the limit as n goes to infinity of 3 over n times minus n plus 3 over 2n minus 3 halves. And then what we're going to do is, on the next line, we're going to multiply that 3 over n into this term. So we still have the limit as n goes to infinity of minus 3 plus 9 over 2n squared minus 9 over 2n. Okay, so then you should recall from your limits at infinity that this term will go to 0 and this term will go to 0. So then the next line is just going to be equals negative 3. And that's your answer. And we can double check this by doing an integral. So you can double check it by saying the integral of 1 to 4 of x squared minus 4x plus 2. So that's going to be equal to x cubed over 3 minus 2x squared plus 2x, evaluated from 1 to 4. So this 2x squared right here, that's because you end up with a negative 4x squared over 2. And then you get the cancellation, right? So when you evaluate this, you end up with a negative 3, which we're not going to worry about because this video is about the limit definition. So there you go. That's how you do a definite integral using the limit definition. And just remember that you're going to need these references for your sums of I, because this is not a complex I. I pulled these references for I and this theorem out of the Stewart Calculus 9th edition on the page number 387 if you're interested. So that's it. If you have any questions, feel free to leave them in the comments. Any concerns, feedback, anything I can do better with this video, feel free to let me know. Thank you.